manageable. In stage 2, the sand pierces the water surface. We check the Weber's number, which is the ratio of inertial to surface tension forces, and find it to be much greater than 1. So surface tension is irrelevant and the sand pushes through. In stage 3, the sand and water form a dense jet due to the buoyancy and drag. As this jet descends, water is drawn inwards, which dilutes the jet and causes it to spread out. This is an animation showing the water entrainment. For simplification, we model the jet as sand-water mixture with a uniform density of rho effective. The reduced gravity characterizes the net buoyancy force on the jet. Applying Newton's second law, the total effective mass times acceleration equals the net downward drop force minus the drag force. The radial number for the jet is around 10 to the power 4, hence the flow is turbulent. This justifies using a constant drag coefficient and using the phi-squared drag equation. Solving the equation as a function of depth z, we will get phi impact, the velocity of the jet when it hits the bottom. Physically, the first term represents the acceleration driven by buoyancy, while the second term is the effects of initial entry speed v0. To find CD jet, we filmed the jet using a high-speed camera of FPS 240 and tracked the tip of the jet using drag curve. For fitting, we extracted beta and found the value of the coefficient. We also note that the jet doesn't reach the terminal velocity, as it requires h to be about 90 cm for the jet to reach 99% of its terminal velocity. In stage 4, the jet hits the bottom and it spreads radially outwards. Using mass continuity, the radial velocity of the jet decays as UR equals V impact times R core over T. We compare the radial velocity of the jet and sand settling velocity. At the impact point, UR is greater than the sand settling velocity, and hence the sand is swept radially outwards. R star is around 20.7 cm, as shown. In stage 5, as the radial velocity of the jet slows down below the settling velocity, the sand will deposit and build the outer rim. For a crater to form, 3 criteria must be satisfied. First, the shield parameter must exceed 0.04, which is a literature value, as it ensures that grains are mobile. Stokes number must also exceed 1, ensuring the grains have enough inertia, while the Battle criterion as mentioned requires the radial velocity at the impact point to exceed the grain settling velocity. For applying for sand at specific water depths, all 3 criteria are satisfied. This theoretical phase diagram shows the 3 regions. The green region is where all 3 criteria are met and the crater forms. The red region is where Battle's criterion fails, as the grains are too heavy to be swept outwards, so a pile forms instead. Using the MTT plume theory, we see that the jet's radius increases linearly with the water depth. The theoretical spreading half angle is predicted to be between 5 to 7 degrees. For the dependence on the funnel opening diameter D0, there are 2 competing effects. A larger D0 gives a wider jet footprint, increasing the crater diameter, yet it spreads the jet's momentum over a larger cross-section, reducing the spreading. Regarding the relationship between the inner slope and the water depth, at shallow water depths, the slope is limited by the angle of repulse. At larger depths, the crater grows wider, while the impact velocity approaches the terminal velocity, making the slope to be less than beta r, which is the angle of repulse. Similarly, against the funnel diameter, as D0 increases, the crater diameter grows, reducing the inner slope, and it reaches a minimum near D star. The slope is limited by the angle of repulse. This is a summary of our predicted trend. As we believe that this model may be too simplistic, though intuitive, I also used numerical methods to model the phenomenon. Using RK4, we can solve the 4 coupled with ODE and find the impact velocity and predict the inner diameter of the crater. For the first ODE, it describes how the jet's radius B grows with depth, in accordance with the MTT plume theory. For the second ODE, it describes how the flow rate Q changes with depth. As the jet spreads outwards, it sucks in the still water from the surrounding environment. The rate at which the new water is incorporated depends on the 2 factors: the surface area of the jet's outer edge and how fast the water inside the jet is already moving. The third equation is essentially Newton's second law. There are two competing terms. The first term represents the driving force, as each falling sand grain exerts a downward drag force on surrounding water. The second term represents the braking force, since the still water outside the jet boundary exerts a force that resists the downward motion of the jet. The fourth equation describes how the grain velocity changes with depth. The numerator consists of three major terms: the effective gravity, a drag term, and a coupling term. The coupling term accounts for the fact that the water itself is also accelerating as it flows downwards, which modifies how the atom mass pushes back on the sand grains. Before we can integrate our four OEs numerically, we need to specify the initial conditions and the water surface, which we define as Z equals 0. For the initial water volume flux Q of 0, phi open accounts for the fact that there is air in the pores of sand. Here, we show the converged numerical output of our RK4 simulation. The left plot shows grain velocity and water velocity involved with depth, with the difference between them decreasing as the water is accelerated by the grains. The right plot shows the particles' radial number decreasing with depth. Moving on to our experiment. We assume that the crater is axisymmetric and that the slow drainage minimally disturbs the final crater shape. Additionally, we assume that the flow rate is approximately constant. The funnel is vertical and the grain size is approximately uniform. Our cell consists of a water tank with a lead jet to set the water head depth H. It also consists of a 3D printed funnel held by a fixed drop height, H air above the water surface. This is a demonstration video of our experiment. Due to time constraints, I'll show it for a few seconds. Yeah. So, and these are our chosen numerical values. These are the 6 parameters and the ranges we test. The 2 primary variables are the funnel opening diameter D0 and the water depth H. These are some of our 3D scans. The final crater has 3 features: a central depression, an outer rim, and sometimes a central dome. Now onto the analysis. Here's our inner diameter versus water depth data, which follows a clear linear trend. The red line is our linear fit, while the green dashed line is per MTT prediction. Both lines have the same slope, confirming the linear trend and the spreading angle. For the inner slope versus water depth, at shallow depths, the slope is fixed at an angle of repose. Beyond about 8 cm depth, the slope drops and the crater grows wider. Here, the data shows the crater diameter generally increasing with D0 and gradually leveling off as D0 further increases. For the inner slope versus funnel diameter plot, the data shows a slight dip near D star of 12 mm. The slope is limited by the angle of repose away from D star, and the dip is small relative to our error bars, so we need finer spacing near D star to resolve it clearly. As the mass of sand increases from 50 to 300 grams, the inner diameter decreases slightly. This is because the additional sand backfills the center. Similarly, drop height has no significant effect on DC or the inner slope. It is because the two effects cancel. A larger drop height increases V0 as the jet is already very close to terminal velocity. The change in V impact is minimal. Additionally, the longer air time can make the sand break up more due to Rayleigh plateau instability, reducing the jet cohesion when it enters the water. Similarly, tube length has no significant effect. We use 2 types of sand, and no crater can be formed for the coarser sand of grain size 6 to 8 mm. It is because the larger grains have higher settling velocity and that no suspension criterion fails. Summarizing, the dominant systematic error across all diameter plots is a drainage-induced increase in the crater diameter. For the slope measurements, noise from the 3D scanning introduces the random errors. To improve, we should measure the crater without draining, for example, by using a laser line profilometer. A larger tank can be also used to prevent the reflection of the displaced fluid. Finally, we can also increase the number of trials from 3 to 5 to reduce the random errors. Finally, onto the conclusion. To summarize, the inner diameter increases linearly with water depth, consistent with the MTT plume theory. The inner slope is capped by the submerged angle of repose at shallow depths, and it decreases below and at larger depths. The drop height, mass of sand, and the tube length have no significant impact. And here are the references we used, and some other more references. Okay, so thank you for your attention, and we would like to invite our opponent for questions.
So firstly, when you dropped the sand from like a point in the air above water, did you consider the effect the air would have on the formation of the crater at the end?
Yes, so you mean the air drag or not the air drag?
Not necessarily drag, air as a whole.
Yes. So you're talking about air that the air cavity formed, maybe like if a speed of very high.
Thank you. So when you're talking about this sand, do you think it behaves at all like a fluid?
As a what fluid?
Do you think sand behaves like a fluid in this problem?
As a fluid in this problem?
Yes.
Yes. Okay. We believe that.
Yes or no, please.
Yes, we can model it as a fluid.
Okay, thank you. When you said you use literature values to calculate different things, do you think these match very well with the characteristics and the variables that you actually, and the materials you actually use in your experiment?
Yes, for some of the, for example, for added mass of water, we have used literature values, and we believe that for most of them, because they are too maybe hard to measure experimentally, it can match with our experiment.
Did you control the size of each grain?
Yeah, when we got the grades, the manufacturers will set a fixed range of grades, and we also measure it to confirm that it's within that range. For example,
how did you measure the grains?
Sorry,
how did you measure the grains? You said you measured it to confirm what's in the range.
Yeah, we use as, for example, for larger grades, when you use a very sensitive caliper.
Okay, thank you.
隨咗算啦，睇唔到啦，咪費事同我哋溝通。
Hey, thank you for an interesting report. Just to summarize our expectations, we are looking for sand that's dropped into water. We want to have a crater that is formed, and for this to be experimented and tested theoretically in a variety of ways due to the different structures of the crater. And for a multitude of parameters to be investigated that would affect this crater. So, to my evaluation of the speed, so in terms of the merits of the theory, there were lots of positions of the crater considered. There was also considering the sand-water mixture and how it is almost fluid-like. This is good because when it's able to mix with the water, it provides a fluid-like substance that has a similar sort of flow, which is what we're looking for, especially given the formation of the jets between the sand, although, as we'll note later, it's not completely a fluid. The noting that it was turbulent flow, and how it would affect the drag coefficient is also beneficial, as this allows for more accuracy in modelling. I thought the quantitative model was detailed enough, and the discussion of the impact point is also quite helpful, as it is largely what causes the jet to shoot up and create the crater. In terms of the problems with the theory, the modelling as uniform spheres was quite problematic, given that it doesn't consider the granular properties of sand, including how they interlock the friction against each other and the irregularities that occurs. Looking at the air, I saw a clarifying question that the air pocket from being dropped was discussed in the report, but it wasn't discussed in very much depth, and that this is also important for the creation of the crater because it affects the fluid that's in the water and thus will change the jet. There was also a lack of qualitative explanation to go with the quantitative explanation, and also the lack of consideration of the crater as a solid structure. So in terms of the experiment, in the merits, the use of a funnel was in general good to ensure an even release. It was also good that it was measured at 7 different points, including the diameter, as this allows for a more rounded perspective on how the crater forms, since it can vary quite a lot in this regard. There were also many parameters investigated, which again enables better problem fulfillment. And there was a quantitative theory experiment link. In terms of problems, there was the assumption of axis and symmetry in the crater, which is likely inaccurate, and there wasn't much consideration as to how things were controlled and how this would affect the error bars we saw, as well as the deviation from the experiment. And there was also lack of an account for how the irregularity of the sand and the great variations that can occur due to not controlling certain variables. And there was also a lack of a qualitative link between the theory and the experiment. So, sorry. So, firstly, thank you for that report. I'd first like to discuss the effects of modelling the sand as the spherical and more as a purely a fluid as well. So, okay, firstly, what effect do you think this would have, especially when we see the crater at the bottom?
Yes. So you mean what effects does modeling the sand as spheres have?
Yeah. Well, yeah. So what do you think it actually does, as opposed to what you might see as spherical?
Okay, so we model the sand as spheres because it is used to simplify calculations, but with also because with the sand grains of the sand will average out and it will be averaged as a sphere. It's very hard to find all the irregularities because for each manufacturer it's very different.
Yes, I agree, irregularities are different. However, the last bit I'm talking about is, so if you consider when it lands at the bottom, so you see obviously it forms that sort of crater. But to do this, it needs to be, say, structurally sound. And the way that it can stay there, as well as, say, pressure from the fluid on it, is by having, say, the grains with friction against each other, having them interlock, that sort of thing. And obviously, you mentioned the angle of repose. A large part of that is due to the sand as an actual granular structure. So because they can interlock with each other and they have friction against each other, it makes its angle of repose higher, which means that the crater will be higher slope this way. So I think that's significant, although I do agree that it is sometimes difficult to model the different sand.
Well, with this because of time constraints, we assume that the frictional, the concept of friction is already included in angle of repose in the derivation of it.
Oh, okay. Yeah, thank you. Yeah, I do agree with that. I just suggest to improve that you more explicitly look at the particular grains. So, following up on this, when you're looking at the crater, and you're saying you didn't consider things like water coming out of the crater, did you consider, say, how the sand could move down, for instance, or did you consider temperature was fixed?
So basically, we in the back-nose criteria, we're comparing the radial velocity to that of the sand settling velocity, and it's higher, it will slide out. And it also depends on angle of repose. Yes, see if it exceeds it or not.
I definitely agree with that, because if you say you have if it's like, say the angle of repose would make it look like this, but then it falls this, again, due to the granular nature of the sand, obviously it's going to have to slide down that way, and that would affect the slope, it could affect the diameter as well. So.
In some extreme conditions, you also observe that maybe slightly higher than angle of repose in some pressure.
Oh yeah, slightly different, because obviously that's extreme conditions. And as you can see, the water generally makes the angle of repose value different. Yeah. So, yes. So, if I move on to my next point, I'd like to look at how some things in the experiment were controlled. Okay. So, let's start with the fact that you used funnel. I agree that this is a good thing to use. Obviously, it makes the diameter of the sand work the same. It should try to make the velocity the same, but you said in your assumptions you assumed that the funnel was vertical. Did you try to make sure this was true?
Yes, so we use the whole spirit level and ensure it's perfectly it is perfectly horizontal. The whole thing, the tube is vertical because it's like it's vertical.
Are you sure that there couldn't have been, say, anything that could have caused it to be, say, not or not perfectly level? Do you think any screws that were holding it in could have slipped?
Not really, because after each time we repeat the experiment, we'll measure it using a spirit level again to ensure it's perfectly vertical. And even if so, it's like very, very negligible.
Okay. Yeah, so I think that that's a good thing, because if you change the angle, it can change the way the sand falls into the water, and ultimately the properties of the crater. I think it would have been better if you had detailed more how you'd control that. In terms of the other control variables, so when I asked you about grain size, you said that it came between a range, but did you consider the effect that how these being different would have on the crater?
Yes, we will need to see a skew towards the larger side or skew towards the small side, but it's really important to both ensure that every sand grain is of the same diameter, so we have to use a tight range.
Yeah, I agree that it is important to show that the sands are the same diameter, because otherwise it affects the friction and affects how the water comes in and how the jet can be formed outwards. I just do think that the fact that they are irregular can still account for a little bit of error. As if we look at your graphs, just any of them mostly, so we notice that the theory seems to be like a bit off, and there's error bars. Do you think there could have been other causes for this besides?
It is because after each trial, we would use a small water pump with the lowest power level to drain out the water and then to conduct a 3D scan of the crater. And so this is why it is vertically shifted outwards. There's an extra line intersect. So between our theory and our first model. So we can try to actually use some suggestions. For example, the laser profilometer to reduce this error, but it's a bit expensive for us.
So that's the error bars?
Well, I mean the shifting from. For the error bars, I think it's due to the random errors I just mentioned in here. The major random errors, as shown, for example, for my first plot. This is mainly due to the non-circularity of the crater, and this is just a rough estimate of the value.
So, in terms of the errors, I think what could be beneficial is to have a greater explanation of why these errors would cause these things. So, say, what do you mean, for instance, by the non-circularity of the crater?
Non-circularity of the crater, because we assume that is axisymmetric, but then in real life it's actually a bit, it differs by a few mm for when we measure using a camera, and we discover that it is a bit non-circular, but it's minimal.
So it's, say, modeled to look like that, but it might actually be closer to something like that.
No. It's if you see our 3D scans, it's roughly a circular shape, but then if you see this diameter may be different from the one we it might be a bit of bonus, but it's very insignificant as shown in the photo.
And what do you think is the cause of the lack of axisymmetry?
But for example, because for example, the flow rates may not be actually really constant, and sometimes in flow, the sand may get a bit stuck, or there might be a slight tilt of the minimum 0 and 0.50 degrees, and then that might contribute to this effect.
Yeah, I do agree with that, because a lot of characteristics of sand means it could fall at a different time, and then when you said they could be unevenly clumped, the water might not necessarily flow through the sand as evenly.
But maybe for the non-circularity, I was meaning that from a top point of view, it's not necessarily a perfect circle. It's definitely your
yes, I mean,
I never saw this before.
Yes. Again, just I think more explanation of this would have been probably better. And now to my last point. So I'd like to see some more qualitative explanation between why your experiment turned out the way it was.
Yes, so onto the qualitative experiment perhaps. For the graphs, maybe we can explain the physical meaning of them. Sorry. Okay, so for example, for the water depth versus the linear diameter, because we see that it's spread out like a cone, we see how what the reason behind the linearity of it. And I'm not sure if you're asking for this qualitative explanation or why the crater forms qualitatively. Are you asking for why the crater forms qualitatively?
Not that as such, but the actual graphs, like the trends you observe. Can we have it? So just go to your one of your first graphs.
Yes. Okay,
if you can.
For example, we can go to any one of them. Which one again?
The crater and yeah. Okay. So why do you think the water depth would lead to an increase in crater diameter?
Why would water depth increase the crater diameter? It's because when the water depth increases, there's longer time for the jet to fall down, and hence they would increase the spreading of the sand, and then you see that there's more spreading with roughly a constant half angle.
Do you also think it could be related to how much water can come in the amount of time? So
yes, it is truly related to how much water.
Yeah.
Okay, thank you very much.
So for concluding remarks, I'd first like to thank the reporter for an interesting discussion. We discussed how there were some potential issues with not considering the granular properties of sand, and we seem to come to a general agreement on the importance of this. We also looked at how certain variables were controlled, including the tilt angles of the funnel, but it was confirmed that this was largely controlled. However, then it would lead to how other sources of error could have an effect, which I don't think were well enough discussed. And then we also looked at how the assumption of axial symmetry was false due to the properties of sand, and how the experiment was positively explained as well, including for the water depth versus diameter. So thank you.
First of all, thank you both for the report and the opposition. I still have some questions. Let's start with the task. The task states that the granules material actually may form a crater-like structure if released in sand in water. Would you say that a hill with a slight hole in it that is actually also achievable in air is distinct to this phenomenon? The opponent, sorry.
Sorry. So you're saying like when it just makes...
Just quickly, would you say that this is the phenomenon described?
I do think it can be described, although it is slightly different.
Okay. Then to the reporter, the task also states that a crater only may form. Did you observe any compositions of parameters that the crater actually didn't form?
We definitely observed that
Okay.
for the parameters from the face diameter and also from our for our larger sand grain size.
Thank you. Also, to the opponent, you mentioned that grains actually behave like a fluid in this case. Would you say that there's limitations for that, for example, the grain size?
Yeah, that's what I was saying. I'm saying it should be modelled as both a fluid and a grain.
Okay, so if you model it as a fluid, I would assume you would take small grain sizes. And would you say that if you release it far above the air, that this distribution with small grain sizes is actually relevant?
Then the distribution as that would definitely be relevant, because if it's too far apart, then you won't be able to get the water coming in.
Okay. Yes, I do agree with that. Also, again to the opponent, the reporter assumed a linear expansion of their cloud in the theory. However, as we saw, the entrance of the water was actually quite small, quite shallow. Would you say that this assumption is still valid?
By the cloud, you mean like the sand that comes out?
No, the height of the water level, which the sand actually falls in. Would you say that this linear expansion of the cloud is applicable?
Like linear expansion of the sand?
Yes. This is applicable?
Likely not, because there's a lot of...
Okay. To the reporter, you say you estimated your errors. Were they statistical errors?
They are both we have both systematic errors and random errors, and there's not
Okay. Also, did you consider the water height relevant at any point?
The water height, yeah, we have a graph of the water depth.
Thank you. Also, did you ever observe like a central hill, for example, for this crater?
Yes. Yes. We will also like to. This is interesting philosophy.
Okay. And one more question: which velocity was used for the Reynolds number determination?
Yes. The velocity for Reynolds number. We had used the initial when the
So, thank you very much, and I would like to start my review on problem number 10, submerged crater. We're all familiar with the task by now, and I will also skip over the expectations for now. First of all, to the reporter, we saw a solid characterization of the problem, meaning we saw a parameterization of the actual crater with the relevant parameters being named, and we also had some variety of parameters that were varied, such as the release to diameter, the water depth, and the trends were also sometimes qualitatively explained. However, we could not quite follow how the crater was actually measured in 3D, and if that was, for example, brought up with using this stepper that we see in the experimental setup, and thus we weren't quite sure on how reliable this tracking actually was. Second, we also thought that there was an insufficient basic explanation for this phenomenon, why it even occurs in, for example, large tanks, why the sand grains slow each other down and the water with it, and there was no experimental confirmation of stated criterions, such as the sand being actually linear expanding, as for my next point. In the clarifying questions, I asked if the water height was actually suitable for this linear expansion model, and in our opinion, it is not, since the entry effects of this phenomenon are actually dominated by, for example, the inertia of the grains, thus not wanting to separate, and afterwards, the expansion only takes place. Thus, we see these theoretical model slides as quite questionable, and we didn't quite see how parameters were, for example, fitted and what literature values were used for our case here. And also the experimental trends were not qualitatively explained sufficiently in our opinion. Now, to the opponent, we saw some quite important points raised, such as the airfall, lacking qualitative explanation, and the rotational symmetry, which we believe is experimentally extremely hard or basically impossible to actually achieve due to inconsistencies in simply water and the grains. However, we didn't quite like the clarifying questions here, such as the data evaluation and the theoretical assumptions were not mentioned here. So, moving on, the fluid-like behavior of sand, we believe this is actually untrue for most grain sizes, and only for very, very small grain sizes we can actually get this fluid-like behavior. However, these grain sizes were not investigated, as they would have quite literally spread apart in the air before the fall, before they already connected with water. Also, the qualitative explanation of the great deformation was again missed, which was agreed upon with our point before. Now to some discussion analysis. First of all, the opponent made a proposition as if the sand is actually granular spherical material and not just inconsistent or wrong. And the reporter replied that they were average outer spheres. We partially agree with the reporter here. However, for example, the assumptions for this model are actually valid, since it's quite literally impossible to model each and every grain differently. However, the different sizes of grains are not regarded, and for a more consistent sphere, we would suggest such glass spheres, for example. Now, to the next point. How was the reproducibility ensured in the setup? We agree with the reporter here. The release mechanism was quite reproducible. However, the volume of sand did not seem to be exactly controlled, and the cones seemed to be slightly tilted in our videos, and thus we could not observe this reproducibility. However, for the next point, the deviation between theory and experiments, we think that the reporter had a point here. However, that could also be an issue if the theory holds predictive power or not. Now, to the opponent's last point, why are the trends the way they are? And the reporter gave an explanation as the cloud increases linearly with water height, and this is an correct explanation. However, stated this assumption is not valid for these low water heights. Thus, we think that task for the reporter was actually partially fulfilled with some wide parameter investigation. However, the basic explanation is quite lacking, and the theoretical models assumptions were not really stated. The opponent also partially fulfilled their task with some important topics raised, with the reproducibility and symmetry being some key points in the discussion. However, there were some more key flaws, in our opinion, that were missed. Thank you.
We would like to thank our opponent and the reviewer for the constructive suggestions. So we have split the whole phenomenon into 5 stages, which is namely free fall, water entry, the water descent, initial impact, and crater formation. We then went using the MTC plume theory and talked about the conditions for the crater formation. For example, including the shield parameters, Stokes number, and Bandow's criterion. We clarified with the opponent over the angle of repose and the positive errors too. To respond to the reviewer, we used RK4 and discretized jet, so we didn't only model it at the single sand grains. And we would also like to clarify that there were no fitness variables except for the CD jet. And other variables, such as for the amount of water, can actually be derived from the, for example, density of the sand, which was experimentally calculated at the start of the experiment. So regarding the fitted variable for CD jet, it was fitted using tracker and it was shown and can be reproducible. And we have also discussed the relevant parameters, including, for example, the mass of the sand, the tube length, the water depth, and etc. So we consider the task to be mostly completed. So. So apart from that, during the discussion, the opponents also raised the question, for example, of the crater, and we would also like to thank our opponent for bringing up this problem, and because and if we show calculations outside, it may be clearer. So regarding the reviewer, we also agree that it may not necessarily be linear for the certain water depths, and we would like to maybe use a more complicated model for accurate analysis. Thank you.
Maybe a question to the opponent. Why does the crater, or does it create also, or is it possible the crater is created when you drop sand in the air, or?
When you just drop sand in there, I don't think it would be created. However, it is possible to form such a crater in air if you sculpt it or something like that, because a key formation is the point of the water jet coming up and forming the crater. Pardon? Yeah, that's my point. So I don't think you would be forming in air, but you could make a similar shape, not by dropping it. So you could form the shape by sculpting it, for instance. Just not the same thing, obviously.
Yes. 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 And for example, this hill-like structure and with only a small radius is actually not, in our opinion, a crater-like structure. It's rather a hill with a little dent in it, and sometimes we could even observe only a hill, and this is due to, for example, the water height not being sufficient and too much volume being dropped at once. Yeah.
To the reporter, I think it was like.
Sorry.
Can you go to slide 43, please? So here in your equation is alpha E. Was it measured or somehow calculated?
This is the entrainment coefficient. This one is the theory that it can be calculated through the standard.
Okay, and it is a constant in all cases.
Yeah, for the theory.
Yeah.
Oh,
Can I ask a reporter, can you go to slide 77?
yeah.
So there are all of these, right, okay. So this looks, where is this from? That's not any of it, yeah, it's not there.
Yes.
What's that? Where is that from?
So this is just a this one is not this one is just a model used for fitting of our of our experiment. So I just found it online. It's just an appendix, not in our main presentation.
What you used it, so where's it from?
We found it online and also used some.
Where is it from?
This,
Where is the reference to it?
for this.
Yeah, I mean, you've got lots of stuff and you've used it.
Yeah, we kind of used
You got it from somewhere.
yeah, we asked others and also used some others to some AI generated, but it's not.
And do you have a reference?
Yes, this one for this equation is not a standard literature equation, so it's just for our own experiments and also from physical principles.
But yes, it's from a paper.
No, this one is from the paper, the D naught plus H2H tangent alpha is FTZ plume theory. It's a paper, yes, this one is a paper.
And is that paper referenced?
We referenced it in, I think, in the reference for MTZ plume theory. It's a standard paper. Let me see. I'm not sure.
Okay. Thank you.
To the opponent, you mentioned the lack of gradient variation. Do you have a solution to that?
Of grain variation. Obviously there is like using a narrower range, but if it's possible to just account for it more in the error, I think it's very hard to use it. Like I heard glass spheres be discussed, but I don't think they produced a crater-like phenomenon as well because they had the reduced friction between them, so they wouldn't form the structure as well. So I think it's just a matter of discussing it more in error analysis as to how that could be like a problem with it.
To the reporters, do you have a reference to that animation in the
Which animation? The water entrainment one? These GIFs are all are from experiments. This one is written by code is HTML. Yeah, this is HTML code. Yes.
哇，你睇唔到呢圖啊？你做乜做咗嚟嘅嘢啫？